you are doing well. Yesterday, I posted a video of rotary embedding, right? RoFormer and then transform with rotary position embedding. So here is the thing: I committed some mistakes because I think I misinterpreted them. So I wanted to clarify upon that, and let's go through. Have a walkthrough to the Hubpace implementation of them, so that we can be more clear upon our understanding. So first thing was that this row former actually it's not applied on the word embeddings part, but it's rather applied on the key value and key value and uh, query vectors, right? So that is one of the thing, and yeah, that's it. And I think that here in the final vector calculation in the earlier video I have applied it on m theta, but it's not m theta, it's actually the word embedding. And the third part is this rotary embeddings are actually applied on each of those features of the tokens, not on the tokens itself. So we would be having a vector of shape d, which is mentioned here, right? X belongs to D, and we apply a rotary embedding on rotary matrix on that part. So here, so a slight change that I have applied it on the sequence tokens, but it should be on the features, token features. So nothing, not much change. We would be just reversing the feature dimension, not the tokens dimension. I had already reversed the token dimension. That's it. And yeah, and the other thing is that I in the last video I had mentioned that we are swapping this features like x1 x3 x5 and so on, and then here also won't it hurt the performance, because currently in the paper it's been mentioned that it's x1 x2 x3 x4, and here minus x2 x1 minus x3 x4 something, minus x4 x3 something like that, right? But we are actually swapping, means we are regrouping them. So won't it hurt the performance? So let me ask you a question, and then I think that this should answer it. Attention is a global operation, right? So it's an n cross n operation. So won't you think that each of the token feature would be attending to all the other features? So, and the other thing is that I need to just explain how I need to means indicate transform that it is an ordered sequence, right? So if I swap, even if I swap them, and they are the parameters which are to be learned, uh, they are not the so even if I swap them and I give them an ordering, I'm still giving them an ordering, right? Cos m theta 2, and so on. Then again cos m theta 1. That this belongs to feature. This is this. So won't it learn in the process of backpropagation, right? So that is the reason I think that in the implementations, if you would see, they would be like swapping them, and I think that's okay, not a big issue, since the final operation which we are doing is global operation, and there would be back propagation as well. So yeah, this was it, and I think that this is good to go. And let's see one more implementation as well, so that we can be more sure about our understanding of this. Time fixing this case. Let's see it here. So we would be actually going through the flow of how this how the role of where actually row former embeddings are being used. So let's say in that normal transfer, what actually are the steps? Here is the steps, right? First of all, tokenization, so that we can result into token, and then we generate the word embeddings, and then we convert it into actually in the original attention is all you need paper. What it is being done is we apply a position embedding with this word embedding, we add them, right? And then we apply normal transformations, transformer attention module, where we take query vector, key vector, and value vector, take the attention between the query and the key vector, and then generate take the softmax, and then generate a valuable contextual representation of the value vector, and then pass it forward, right? Means apply one more MLP and then pass it forward. That is the simple part. So instead of that, some modifications are being done actually. So we would be looking into that to generate the word embeddings, and then we convert it into query, key, and value vector. And here is where we apply the rotary embedding. So this vector actually can be query and can be value vector, key and the query vector. Let's see. So yeah, Hugging Face. I also have one more implementation. Look at wings for no. rotary embedding. We would be seeing both of them. Both are talking about the same thing, just in some different way. But we would be looking into that, so no issue. Gonna be it will be a bit lengthy, but yeah, hold on. Mm. So, in order to check it, RoFormer model, this is where the things come, right? And then we apply a classification head, then it adapts itself to a classification task. So here is the thing. We would be so how our thing initial has RoFormer embedding is there and RoFormer encoder are there. That's it. And what are the input IDs? The same tokens. Attention mask. If we are using padding, the rest of the tokens would be zero if they are not actually with the pad tokens. Token type IDs 000 111. If there are two sentences, then it would be zeros and ones. If there is one, each of those token whether it represents the first sentence or the second sentence. What are input embeddings? Input embeddings comes from the word embeddings. If you are using separate word embedding vector. Encoder hidden states is actually if you want to use it as a decoder, I think. And past key value attention. If you want to output attentions, output hidden states, return done. Right. Sure. So the what? How are the things being calculated? See, embedding output is actually equal to self dot embedding. These are few checks, okay? Because they have to serve it to a lot of people, so they can't be like yeah. So mistakes. So self dot embeddings. So this is the part, and then the second part is passing it to self dot encoder and then outputting it. Let's see how are these row former embeddings being calculated. So RoFormer embedding actually comes from have just word embedding in the token types embedding, nothing more. Right? That's it. So you would see that will pass firstly through input embeddings is actually coming from the word embeddings and yeah, and then the token types embeddings actually are zeros. Zero zero means present in the same sentence. If it is none, then and yeah. So this was the first part, and row former encoder is the second part, right? So here is the thing. So, there are two things: self.embed positions and row former sinusoidal position embedding, and the other is row former layer. So I would be let's see how it goes. First of all, this thing is actually the same. We would be actually uh, initializing the sinusoidal position embedding. Remember that in the row former paper as well, they adopted the thing from the attention is all the n theta part from the attention is all unit paper, right? So that is where this thing comes from. Let's see how it. Let's explore how this is all about. Mm, ठीक है. So it's an actually inherited the embedding class. The initialization method is being given identical to the XLM create sinusoidal embedding. Expect the features are not interlude. Interlude means remember that in the attention is all in paper. It was like odd positions have cause or even position has signs or something, or vice versa. So that is the thing. Torch dot arrange and yeah, the cause feature are in the second half of the vector and the signs are in the first half. Position embedding np dot array. So this is the same thing, right? Base value divided by this the part and yeah, np dot sign and np dot cause. So they have actually they have generated the sinusoidal embeddings as similar to this, right? Np dot sign of the output part. So it would be like the first half would be sine and the second half would be cos. Right. That is the part. And how are they utilizing it? That's the thing which we'll be seeing next. See, layer module is so we have come across here, right? Sinusoidal position embedding comes from this. And now for each of those layers, self dot layer, which is equal, which is a row former embedding, we have actually apply a row former attention and we the same thing, right? Row former attention comes into play. Row former attention is actually the row former self attention. So here is how the things are going. The first remember that's in the sinusoidal initialization what was the thing that first were First were sines and the second were cos. But I think this is wrong. Let's see. Key, query key and value vector, right? This is the thing. And see, if sinusoidal position is not null, remember that how we have done it. The first part was sinusoidal and the second part was position embedding. So what we do is we apply the rotary position embedding on that same part, sinusoidal position. And how are they sinusoidal? This is the argument which comes in. This is the same if you would see. Uh, chalo. So how are they? Let's see how it is being defined. And this is the main part where we want to. So what we do is we first chunk them sine and cos. Remember that first part was sine and the second part was cos, right? So this is what we chunk them and this is the last dimension. Now sine pose equal to we concat them across the last dimension. But I think here is the thing where I think them. I really am not sure if this is correct. See, theta naught, theta one, theta two to theta d by two minus one. If we stack it across the last dimension, it would actually be theta one, theta two up to then again theta one, theta two. Right. So let me explain it here. If you want to see. Uh, I'm not sure if this recording is again. We have that this sign has a shape of batch size, comma sequence length, comma hidden dimension, right? Hidden dimension by two, right? And similar is with the shape of cos. Let's say it like this. If I keep batch size one, sequence size one, and this. So if I say ones and if we initialize it across ones and twos and we concatenate it across the last dimension, right? It would be out, output equal to output dot shape. Uh, I'm concatenating it across the last dimension, right? Uh, what is the shape of twos? I need to concat it, not stack it. Oh, got it. They have stacked it and they have not concatenated it, right? So this is where the thing comes that they have actually done theta naught, theta one, theta two, theta d by two, and here is the thing, right? And then the same thing goes with the cos, and then they would be reshaping it. I have done concat, right? Okay. I identified my mistake, and then the thing comes that now here is the thing. Now what will they do is कि query में they firstly take the odd tokens and then they concatenate stack it on the so I think then that means we can also do it. Hmm. They have stacked it and then they have actually reshaped it. So reshape में the thing would be um, I'm not sure if it actually works, but I think it would work. So the thing is that they have stacked it. Stacking and concatenating are actually like they are s- they are somehow similar but not actually similar. So this is why they have done toss dot stack and cos and sine. So this is where I think I have missed it. And toss dot stack and the same thing is being applied here as well. So let's see it here. We would first rotate this across the take this represents all the other dimensions and the last. So in the last dimension they have taken the odd features first and then this even features first, stacked it, and then what they have done is let me explain it like this. See, we toss dot stack. Now see, it would actually be 1 to 1, 1 1 1. See, yeah. If we even reshape it, I really am not reshape as. I really am not sure if this is actually would yield this the same thing. Theta 1, theta 2 like this. It should really be like theta naught, theta 1, theta 2, theta, and then again the same part. So yeah. And then let's see it here. Take the odd ones, take the even ones, concat them, stack them across the last dimension. Ah, axis. Hmm. Now it works. Right. So if we stack it across the last dimension, it actually works. And now the thing becomes easy, right? So this is where I need to improve as well. If we can stack, let's do it here. So toss dot stack. Now toss dot get this should work. Toss dot stack x is equal to -1 dot view vector dot size 0 vector dot size to -1 comma -1. Same thing. Final vector, and if we rotate them, must be a tensor and not tuple. Uh, that should be view. Thank you. So this is how the things are going. So yeah, it also stack along the last dimension and reshape it. So this is how this interleaving thing also works. And so this was the thing about the values vector, and the same thing is going here as well. This is rotary embedding. Apply rotary embedding. So apply rotary embedding is like this, and so we apply. So this is the first part, and this is the T left, T and T right, third part. T left, T right, and T. Start index actually is like uh, let's say that T left and T right are actually the end, right? Root dimension. So it would be actually rotating this half part. How this rotate half part was the same thing, stacking and then that. I actually did concatenating, but actually it should be stack. Interleaving part came into picture, and yeah. So so in my implementation, there was a mistake of this X1. I was stacking them together, and then so this was it. I think it cleared a bit of confusion about how this interleaving things work. Yeah, that's it for the video. Thanks. Bye.